Good evening, everyone. Good to see all of you here this evening. I think I know all of you, but in case I don't, I'm Jerry Schubel, and I want to acknowledge our sponsors, the Gazette newspapers and the Long Beach Westin Hotel. Without their support, we would not be able to bring you this continued list of very distinguished speakers. And tonight we have with us Dr. Gary Griggs. He's going to talk to us about climate change and sea level rise. This is another lecture in our Ocean on the Edge, Top Ocean Issues series. This one, again, falls in the category of land-sea connections. Last week, you heard Stan Wilson from NOAA. He also was talking about global climate change and sea level rise. But you'll hear a very different perspective this evening. This one comes from a geologist, a very distinguished geologist, and he's going to be talking about our shoreline here in California. What some of the prospects are for the future, and what people who own waterfront property should be thinking about. It's right. Dr. Griggs has been a professor of earth science at the University of California, Santa Cruz since 1968. That was the year that he got his PhD from Oregon State University. He still holds the record for getting a PhD in the shortest amount of time between the bachelor's and the PhD, 3 years, which is quite remarkable. He is also the director of the Institute for Marine Sciences and the chair of the University of California, the Whole System Marine Council. He served for 15 years as a geologic advisor to Santa Cruz County. He has consulted widely for local, state, and national government agencies, and his research and his teaching over this time has focused on coastal processes, hazards, and coastal engineering. His most recent work has focused on coastal hazards and land use planning along the California coast, and it includes work on coastal erosion, littoral cells, sediment budgets, coastal protection structures, and their effectiveness and their impacts, and also the effects of large coastal engineering structures on the shoreline. Since 1991, he has led an effort to develop a major marine research and education center at the university's Long Marine Laboratory, and they also have a science center and an aquarium. He's a distinguished author and scholar. He's written or co-written over 150 articles that have been published in professional journals, as well as several books. And among the titles, we have Geologic Hazards, Resources, and Environmental Planning in 1983, Living with the Changing California Coast, 1985, California's Coastal Hazards, a Critical Assessment of Existing Land Use Policies and Practices, 1992. And he told me earlier this evening that he's starting work on his next book. So when he gets that one done, we'll have him back to speak with us again. It's a great pleasure to welcome Gary Griggs to the Aquarium.
Now, the challenge is to be as efficient as Jerry was introducing me as we get this up and going here. We can substitute climate change for global warming if it makes you feel better. That's fine. And I'll try to put in some positive words tonight. Certainly the issue of climate change and global warming is very different if you happen to live on the coast, or you happen to be in politics, or you happen to be a geologist. And as a geologist, there's never been a question that the climate has been warming for 18,000 years since the last ice age melted, the last ice age ended. And the issues we've been dealing with today are more perhaps what the human impact on that has been. But what I want to do tonight is try to bring that up to the shoreline and talk a bit about the kinds of things that have happened, what we know drives this, and where we might go from here. And it's clear, has been clear for a long time as people began to explore the Earth, that certain parts of the globe were much warmer than others. We've got the tropics and the poles, which is really a function of how much sunlight they get. But it wasn't until the early 1800s that a few people began to think that maybe the Earth's climate had changed throughout the history of the Earth. And some of the early observations were the finding of things like what we call erratics. And these are these isolated boulders that were found in fields in Switzerland and the mid-continent of the U.S., Scotland, that didn't match the rocks that were found in that area. Did they get transported by floods, by glaciers? They got there in some other way, and how did they get there? There was a European, actually a Swiss naturalist, who came to the U.S., was at Harvard for years. He had all those characteristics that most university professors don't. He was outgoing, articulate, charming, ambitious. And as he started to look more carefully, he began to make the observations that, in fact, if we looked at some of these locations over time, glaciers had, in fact, retreated. And if anybody or any of you are from the Midwest, you'll realize that the Great Lakes were carved out by glaciers. Glaciers came down into Kansas, Nebraska, and Illinois, and it produced not only a lot of the landforms, but the soils that were left behind. So he put out the odd notion at the time that, in fact, the Earth had undergone ice ages when glaciers had expanded. When it got cold, when it got warm, they had retreated again. It took a little while to understand why that had happened. It was actually an Englishman named James Kroll back in the 1860s, but later sort of worked out in more detail by a Yugoslavian astronomer named Milankovitch. And he discovered, and it's interesting to find people were doing this 150 years ago, that in fact the distance between the Earth and the sun determines how much heat we get. But that distance doesn't stay the same. In fact, there's 3 cycles. One is that the Earth actually tilts on its axis, and it has a couple of cycles. We call that the precession of the equinoxes, one about 19,000 years long and one about 23,000 years long. So when we're tilted away from the sun, that area is a little bit cooler, and we're tilted toward the sun, that area gets a little bit warmer. There's also a wobble of the Earth on its axis that has a cycle of about 41,000 years. And the plane or the orbit of the Earth around the sun isn't circular, but it's eccentric, and that has a cycle of about 100,000 years. So when you put all those cycles together, so this is going from the present back 200,000 years, 400,000 years, 600,000, 800. This would be 1 million years ago. This is the tilt. And so in each case, when it's up, it would be warmer. At the bottom of this, it would be cooler. So this is from the tilt. This is from the wobble. This is the eccentricity. So those are all working together. When you add them all up, you find a pattern which has just been called solar forcing, which is how warm it is or how cool it is on Earth, depending on how far we are from the sun. When you put this together, you realize that we have these ice ages that have been recorded throughout time. This is just going back 1 million years, but we can see the peaks of the ice ages. The cool periods correspond when we're generally further away from the sun. It's colder and we get closer. It gets warmer when we go out of the ice age. So those climate changes have now been recorded in a number of different locations. In the deep sea, I'll talk just a little bit about each of these, in ice cores from Greenland and Antarctica, and also in glacial deposits, such as we talked about earlier. So we've now been drilling into the ocean floor for about 40 years with the program that was first called the Deep Sea Drilling Program, and then the Ocean Drilling Program, and several other renditions, basically using the same technology we'd use to drill for oil on land. And by putting that drilling rig on a ship, we have now gone down in water depths of as deep as about 25,000 feet and drilled as far as 5,000 feet into the seafloor, bringing back cores of sediment that's sort of the history book, the record of what's happened in the overlying water. Whether it's warm water organisms or cold water organisms, they will settle to the seafloor as they die, just as they do right offshore here in the San Pedro Basin, and they're recorded or preserved in the sediments. So oceanographers, geologists can go back and look at those fossils, do dating on them, look at their chemistry, and find out whether they represent warm or cool periods of time. And we've now drilled back about 200 million years. So the oldest sediment on the seafloor is about 200 million years old. Does anybody know how old the Earth is? Good. 4.6 plus or minus. So what's left in the oceans today is only a small piece of that. We can't go back further in the present ocean basin because the ocean basins keep getting recycled. We can go on land, but this is a place for a pretty good continuous record. We've also now cored in these deep ice caps in Greenland and Antarctica, and we've gone back roughly 110,000 years in Greenland and 420,000 years in Antarctica. And by looking at the chemistry or the isotopic signatures of those ice layers, we can actually get a record of past climate change. And if we put those all together, again, going from 0 today, back 100,000, 200,000, so forth, we can actually see when it was cold and when it was warm. So climate has changed throughout Earth history. You can get that from fossils, among other things, from the deep sea floor. And that's going to be reflected in sort of the volume of the oceans as well. So as the temperature rises, the ice caps melt, glaciers retreat, and that water goes into the ocean. So this is just a plot that goes back from the last 1,000 years. So this is the present, the year 2000, 1800, the year 1600, and so forth. And we can see in both these cases we're using sort of 0 as the average temperature for this roughly 30-year period, from about 1960 to 1990. So that's the 0 here. And this is sort of the departure from that. So for the last roughly 2,000 years, it's been cooler than it was in this 1960 to 1990 period. And all of a sudden now it's getting significantly warmer. These are in degrees centigrade, so these are tenths of a degree centigrade. And if we look at just the last 140 years, we see it's been cooler, warmer, cooler, and now it's getting warmer again. So just try to put that in some perspective. And again, realizing that human activity really didn't enter onto the scene until somewhere in the maybe late 1800s with the Industrial Revolution. So all of this fluctuation occurred way before humans were around to have any significant impacts. So as it gets warmer or cooler, glaciers, advance and retreat, and sea level rises and falls. So we can now go back various ways. We can not only look at the temperature over time, and this is where we are today. We let this be the average of the temperature over the last 15 years or so, 20 years. In a normal chain of events, it looks like maybe it would begin to cool down and we go into another glacial period. But the question is sort of what's going to happen next. If we go back 125,000 years ago, it was actually warmer and sea level was about 20 feet higher. So that's not new. It's been much warmer than it is today. Sea level has been much higher. The difference was that there weren't humans around in a civilization that was built on the shoreline and was very dependent in terms of agriculture and other things on where sea level was and what the temperature was. So if we go back to the end of the last ice age, about 18,000 years ago, something like 3% of all the ocean water, about 10 million cubic miles, was piled on the land as ice caps and glaciers. It covered Alaska, Canada, the Northwest, New England, the Midwest, Scandinavia, and so forth. As that melted, well, at that point, we took all that seawater out of the ocean to form the ice caps. We dropped sea level about 350 feet below the present. So if we look at the North Sea, for example, here's London, here's Paris. This was the shoreline 18,000 years ago. So we could walk, we didn't need the channel. We could walk from London to Paris. And we know that from, in fact, looking at sediments and preserved fossil remains, things like freshwater peat that are now below seawater in the English Channel, things that we know live in shallow water like oysters. And if we looked at all those samples we've collected, and this is going back from the present, just back since the last ice age melted or ended about 18,000 years ago, for every one of those samples, we would go out here with a ship and collect out on the shelf. We can get an age. We can date that by carbon-14. And if we know whether it was freshwater peat, that it might have been a little bit above sea level, or an oyster reef that might have lived very close to sea level, we can actually put a depth or an elevation on that where we found it. And by doing this in various places around the world on coastlines that are stable, we've actually been able to develop a sea level rise curve. So this is what sea level has done over the last 18,000 years. So again, humans didn't appear in any significant way to have an impact until over here someplace. So this is all natural. It's been warming, ice has been melting, sea level has been rising. So here's where we are today. If we look globally, or even in the U.S., we find sea level isn't rising at the same rate everywhere. You say, well, why not? Well, in part it's because the land isn't staying stable. The land isn't stable. If we look at tide gauges in Alaska, and until very recently, our records of sea level rise were coming from tide gauges. We have one in Long Beach Harbor, we have one in San Diego, and so forth. In Alaska, over the last 100 years, sea level has dropped 50 inches. You say, well, how can that happen? In San Francisco, it's risen about 8 inches, which is about the global average. And in Louisiana, it's risen 38 inches. Is this the same ocean? Okay, the land's moving. In Alaska, because we covered it with ice during the last ice age, that mass of thousands of feet of ice depressed Alaska. That took thousands of years. We melted the ice, and the Earth doesn't rebound as rapidly as you jump off a boat. It actually takes a long time. So Alaska is still rising, as is Scandinavia, as is Scotland that was glaciated. So in fact, what's happening in Alaska is sea level is slowly rising, but the land's rising much faster. So in fact, if you're standing on the beach in Alaska, sea level is actually dropping relative to the land because it's rising so fast. San Francisco is just about the global picture, meaning it looks relatively stable. Louisiana, because of all of the thousands of feet of sediment on the Mississippi Delta that have come out of the Mississippi Basin, New Orleans is sinking. The Mississippi Delta is sinking. So here we've got a real problem. It's not just 2 millimeters per year or 8 inches per century. It's 4 times that fast. It wouldn't be the place I would buy coastal property today. And if we look a little more locally, we've got Santa Monica, Los Angeles, Newport. A little bit of variation. So Santa Monica is a little lower than the global average of 2 millimeters a year or 8 inches, so it's a little bit less than that. Los Angeles is a little bit less. Newport Beach is about the global picture. So if these are lower than the global average, it means the land's rising a bit. So we're sort of in the range of the global average here. And it depends also on how many years of record we have. Most of these go back, well, LA goes back to 1923, and so we've got slightly different periods of time that are included. So this is what we've measured for the last 120 years or so, about 2 millimeters a year, about 8 inches in 100 years. But this last little red line here is from satellites. So tide gauge records are at the mercy of what the local landscape is doing. Satellites are independent of that. I do not understand how we can get an overall measurement of the elevation of the ocean down to 1/100th of a millimeter from a satellite. But I'm going to trust that the people that are doing that know what they're doing. But what it does show is, now that we've eliminated sort of some of the other variations from tide gauge records, is in the last 13 years, the number has gone up from 2 millimeters a year to about 3 millimeters a year. That doesn't sound like much. It's a 50% increase. So is that a reflection of a trend that we should be concerned about? This Intergovernmental Panel on Climate Change, which you've probably heard about maybe last week or the last talk, is this international group of perhaps 3,000 scientists trying to come to agreement on what's happening with climate. Their estimates for 2100 range from about 1 to 2 feet higher than the present. But what they've done basically is took this curve and just extrapolated it out using some slightly different variations. They haven't accounted for things like the Arctic ice melting, the Antarctic ice sheets breaking up and melting, methane being released from permafrost, and a whole series of other things. So most people, I think, would say that that is a pretty conservative number. But you're probably seeing things like this in the paper pretty regularly. This is sort of a long-term average of the Arctic, and this is what the ice cover looked like in 1995, 6 million square kilometers. People have been surprised that all of a sudden there's now a ice-free Northwest Passage that we never had before. So 12 years later, this has gone down by about a third. That's significant. Something's happening. So that wasn't included, that melting wasn't included in this IPCC study. Well, you got to have a little humor. So bringing that down to the coastline now, I was really impressed with the new exhibit here of the 10, how do we call it, the 10 major problems facing the ocean, and I'm honored to be invited to talk about one of those, but they have a plot that's a satellite view of the Earth at night, and this is the U.S. part of that. But what's interesting, if you look at the global picture or the U.S. picture, is even places that you might not think are particularly highly populated, the coast of Central America, the whole coastline is lit up by lights. The U.S. is even more impressive. So we look at, Southern California, almost solid lights up to maybe the Big Sur coast and so forth and so on. And the East Coast is more so. So what's clearly happening is people are moving to the coast. And I, would ask you all, well, I won't ask you, but would you rather live in Long Beach or, Fresno or Long Beach or Omaha or something? I mean, there's a reason people want to live on the coast. A lot of reasons. So most of the fastest growing cities, the most densely populated cities and counties are in the coastal zone. And it seems like we're on sort of a collision course. More people moving to the coast, but sea level is continuing to rise. This happens to be the tsunami in the Indian Ocean a couple of years ago. Lots of people living very close to sea level. In fact, a lot of reasons people live here. There's jobs. The climate is better. But we now have about 100 million people globally living within 3 feet of sea level. So if some of the reasonable estimates of how sea level may get by 2100 in fact materialize, we're going to have to figure out where to put 100 million people. We may have more people not to deal with at the time. This is Mission Beach, sort of a series of storms and odd weather conditions that hit in 1988, 20 years ago. I don't know. To me, this is sort of this wonderful microcosm of, it looks like it's all coming at once. And it's almost like they're going to hold it back. They do what they can. But why is 2 to 3 millimeters a year of any concern? Well, first, I think it seems to be increasing that rate. Second, you got to sort of look a few more years out. I think these are long-term problems that are going to get worse for our children and their children. And second, again, we have a lot of people living quite close to sea level. In fact, one of the desirable addresses in Malibu is Sea Level Drive, which I find humorous. So here we are in Long Beach. If we look at the offshore seafloor, we can get an idea of where sea level used to be. And the point I want to make here is sea level continues to rise or accelerates, there's going to be two issues we're going to have to deal with. And that depends on what the local topography looks like. One is inundation, simply flooding, like that picture of Mission Beach. If you're within a foot or 2 or 3, now remember, it's not just mean sea level, but it's waves, it's tidal fluctuations, it's surges during El Nino events, and as the seawater warms, it actually gets less dense, so it takes up more volume. So it's not just a nice flat surface of a lake, but there's other things going on. So one is inundation. The second is cliff retreat. As the sea level rises, the shoreline is going to have to retreat with it. So if we go back 18,000 years ago, that was the shoreline. If we go out to the edge of the continental shelf, this is this sort of gently sloping chunk of land that's now been submerged. So this is sort of where sea level has dropped to periodically. This would have been 18,000 years ago, sea level was 350 feet lower. So that was the beach. All that real estate is gone. Sorry if any of you are real estate agents. I don't think we're going to get it back anytime soon. And we can actually see as sea level rose, this is where the shoreline is today. So depending on, and we can see the Long Beach area, sea levels rising over the subsequent 18,000 years, and here's the coastline today. So with this scale, you can see here's, say, 4 nautical miles, or say 4.5 statute miles. So the shoreline is retreated 4, 6, 8, 10 miles, depending on where we are over the last 18,000 years. Now, fortunately, there weren't any permanent structures out there then. And what we built today, Jerry and I had a bite to eat before this, and I looked out at all these facilities, there's a lot of stuff out there. So, well, what do I say about this? It's definitely going to be a concern in low-lying areas. California is beginning to think ahead, and one of the things I will say with all the other problems I'm talking about tonight is California, I think, is probably leading the country in terms of looking at the ocean, ocean policies, ocean planning. None of those are easy and none are straightforward, but we're now, agency by agency, beginning to try to look at adaptation or mitigation of climate change and sea level rise. There's an organization in the San Francisco Bay region that Jerry's been involved with called the Bay Conservation Development Commission. Because so much of San Francisco Bay is so low, they decided to look ahead. They have very accurate topographic maps, and they just projected a 1 meter sea level rise, which is what many people feel is reasonable by 2100. So this is the San Francisco airport. This is the main terminal. These are the runways. This is Highway 101 that runs through there. So you might say, well, why did they build the airport within 3 feet of sea level? Well, it was all built on fill, so they had to bring in dirt from someplace else. I mean, why make it 40 feet above sea level? They just got it as high as they needed to be able to land airplanes on it. And if you go across the bay to Oakland, it looks exactly the same because the Oakland airport was built on fill. So this isn't going to happen tomorrow, but it's certainly within the range of what we should start to think about. And this is something I picked up. This is Newport Beach. This is a bit more, maybe 5 feet or so of sea level rise, and you can see how much of Newport and Balboa are within 5 feet of sea level. So we could do this in communities around the country and around the world. That's beginning to be done, and that's obviously a lot of valuable real estate. So, without threatening anybody, I mean, it's clear that there's a lot of communities in Southern California that are quite low. They're built virtually on the beach. And one has to think that this sand got here from wave activity. So it hasn't been that long since the waves have been, and some of you may live in these houses, but clearly a lot of Southern California is very close to sea level. I mean, this is sea level here. If we look at Malibu, which is a really interesting place, there's not only places that are built almost on the water, but there's places that are built out over the water. And I'm not quite sure what the lot of record was that they built on. But Malibu is a place unto itself. But they have some real concerns for the future. So what does this all mean for people who live on cliff tops? I used to see cartoons like this and sort of chuckle and say, well, that doesn't really happen. Well, it does happen. What does it mean is that, first, an awful lot of Southern California, particularly northern San Diego County, Orange County, the cliffs have been almost completely urbanized, the cliffs and the bluffs, but sea level, as it continues to rise, is going to continue to move those bluffs backwards. In this case, actually, that house is no longer there. There's other reasons why, but that's the kind of thing we're probably going to see more and more of. Again, this is one of those jokes. I got a better view when the house fell in the ocean across the street, but that's precisely what happened in Pacifica, south of San Francisco back in the 1997-98 winter, where the whole oceanfront street went onto the beach there. And there's a place like Palos Verdes where we built, right on the edge. Actually, these are pretty hard rocks. I think this might be, I'm not sure exactly what the formation is, but clearly you can't resist another 3 or 4 or 5 feet of sea level rise forever. So there's a lot of places that are begin to have to respond. And some of the most problematic stretches of Southern California are where the beaches are narrow and therefore the waves attack the cliffs much more frequently. So we've got not only a problem of there isn't much buffer zone, but that means erosion is proceeding at a more rapid rate. And this is pretty high density development. These aren't little beach shacks. So one begins to think about what's involved in dealing with a sea level rise. You can see the problem gets a little more complicated. And there's also the issue that we'll talk a little bit about is, can we just protect the coastline? Well, along the California coast today, about 10% of the entire coast has now been armored, whether it's seawalls, riprap, revetments, bulkheads. In Southern California, the 4 Southern California counties of San Diego, Orange, LA, and Ventura, 33% of those coastlines have now been armored. So there's a huge investment in rock and walls, but I think the question, well, we'll talk a little bit more about that, is how much sea level can you hold back with a rock wall? And then there's places scattered along the coast where it isn't just rock by rock and grain by grain, but where we have huge landslides. This is down in Torrey Pines, just north of Scripps. But it's interesting to find people are still building houses immediately landward of that. And there's a couple others closer to here, Portuguese Bend and what's called Sunken City, which is actually another big rotational slide not far from here. The whole coast doesn't look like that, but those present different sets of problems. And clearly, sea level rise removing the base or the toe of this is going to help destabilize the overall failure. We've done some work recently. It's sometimes hard to give an erosion rate of 6 inches per year, 1 foot per year. It doesn't really mean anything. It's like 2 millimeters per year sea level rise. So we've looked at some old historic photographs and then tried to see how that's changed over time. There's a state park in Santa Cruz, the northern end of Monterey Bay, called Natural Bridges State Beach. This is a picture taken in 1880, and we just sort of fade that into 1972, and then this is 2006. So we can actually see over, a generation or 2 or 3, that process taking place. This is another, that took place over 100. This is a place about 4 miles north of Santa Cruz, a surfing beach called 4 Mile Beach. This picture was taken in 1969, and you can see there's no arches. It's actually pretty resistant rock. But if you look at this location, by the mid-70s, that arch had opened up, and by the early 90s, that had collapsed. So this is a rural area. There's no houses there, but now within 25 years, we've seen significant retreat. So it depends on the wave climate, the storm history, the nature of the rocks, and so forth. Does anybody know, do all of you know about this website, CaliforniaCoastline.org? If you haven't looked at it, it's an incredible resource. I know the people that did this, they live up in Santa Cruz. They sort of got started doing this in sort of a conservation role. People were saying, well, if we knew what was on the coast today when somebody did something illegally, we could actually record it. So they said, okay, we'll just fly the whole California coast and take pictures. So they got a helicopter and they flew the California coast in 2002, taking overlapping digital GPS-based high-resolution photographs. And where most people found out about it was they will put on the website, when they pass a certain location, it'll say the Queen Mary or Barbra Streisand's house. Well, Barbra Streisand wasn't happy about that, so she sued them. If you go on the website, they have a story of the lawsuit, and then there's a copy of a check that was Barbra Streisand paying their legal fees for what was deemed a frivolous lawsuit. But they actually flew the entire coast in 2002, 2004, 2006. So you can point to a map and do Long Beach or San Diego or any place on the coast, and you get a sort of a proof sheet of little strips. You can blow that up to 3 by 4 inch, and then you can blow those up to 36-inch square photographs. You can see what kind of lawn furniture Barbara Streisand has, if you were really interested. It turns out I had photographs, colored slides taken in 1972 and 1979, and we got together and we scanned 12,000 35-millimeter slides, put them on the website, and the Coastal Commission had a set from 1985. So you can now go on this site, hit time comparison, and see 36 years of coastal change. I got a call about a year ago from a local realtor. This is a place called Capitola. And he said, I have a apartment complex in escrow, and somebody said that I perhaps should call you to see if there's any problems. And I said, well, where is it? And he told me the rough area, and I said, oh, is it the Antigua Apartments? And he said, well, how did you know? I said, oh, I work in this area. So I said, are you at a computer? And he said, yeah. I said, well, type in CaliforniaCoastline.org, which he did. And I was just about a step ahead of him, and I got the image number of this photograph. And I said, just type in this number. And all of a sudden, I heard this sort of gasp at the other end of the line. I heard this guy say, oh, shit. So he had no idea. He had a buyer. They were standing on these decks looking out over the ocean, but he had no idea, because you can get down here and look at it, but he had not done that. I don't know whether he sold it or not. But it's a really incredibly useful tool for finding how the coastline has changed if you're thinking about buying a piece of oceanfront property or selling or whatever. There's a pretty good record there of the last 35 or 36 years of how the coastline has changed. So in addition to sea level, we've got another cycle we've now been able to understand over the last 30 or so years. And it turns out the Pacific Ocean, we know now, undergoes some significant climate changes as a result of warming and cooling, water temperature differences, wind direction differences, and we have something we've now called the Pacific Decadal Oscillation, which is this sort of oscillation in the climate in the Pacific that may last 20 or 30 years. And it turns out we had a period from about 1945 to 1978 that, and this plot is dominated by blue. Those tend to be cooler La Nina cycles with not as much rainfall, not as many coastal storms, a little more benign climate. This is the period when most of the Southern California coast was developed. Following World War II, servicemen came through California, the way of the Pacific, said, I want to come back to California. Population went up, people built on the cliffs, on the beaches, on the dunes. And in 78, we had a change. We went into what's now called a positive phase of the Pacific Decadal Oscillation. More El Nino events, and you probably remember the ones particularly of 82, 83 and 97, 98, but there's been some others. And in general, what that means is water's warmer. Not only we get different fish and organisms in the water, but more evaporation, more coastal rainfall, more flooding, more landslides, more coastal storms that generally come from the west and southwest. So these have been a number of damaging coastal years that people weren't really prepared for. So the question sort of out here, it looks like we've now flopped into another negative phase. We're not sure. And we also don't know, as climate changes, it gets warmer, whether we're going to see more El Nino events. So those are some of the uncertainties, and I'm not sure we know the answer to that yet. So what we see along the coast today is more people and more development moving towards the coast, and on the other side we have a rising sea level, coastal erosion, El Nino events, tsunamis, hurricanes, etc. And in a normal period, in the middle of summer, you'd look at this and say, wow, what a great place to live. But generally in the winter, these places have some severe problems. Could I say that any other way? So we basically, this is also Malibu. So, if you don't really have, we always say you don't have to be a rocket scientist. I don't know why. You say you don't have to be a marine biologist. You don't have to be a geologist. This is a stream coming. So this is sort of an alluvial. This is an alluvial fan at the mouth of a coastal stream, and this is the beach. So it's a tough place to try to survive over the long term. So I say we have 3 large-scale choices. One is denial. One is adaptation. We know sea level is going to rise. What are we going to do about it? And the third is mitigation. Can we do anything to slow it down? So I'm just going to touch on politics a little bit. You warned me about that, Jerry. I'm just taking it out of the newspaper. Adaptation would be we can retreat, we can move houses back, we can armor, we can try to build structures, or in some cases we can elevate the structure. Can we elevate the San Francisco airport? I don't know, but they're probably thinking about that. So here's an example of retreat. These are some apartments. They were damaged during the Loma Prieta earthquake. The coast is eroding in it. They took down 6 apartment units. So that's one kind of adaptation. Retreat. This, if you don't know, this is Isla Vista. This is student housing at UC Santa Barbara. I actually showed this apartment in the first slide. There are a lot of places where retreat may be the only long-term option. This is that structure up close, and within the last year, it was deemed unsafe. And I think it's probably because there was 400 fraternity guys with beer kegs up here jumping up and down on the deck. So it's not there anymore, and they've been retreating. So that's beginning to happen. Most people aren't ready to give up their oceanfront property, but there are places like this that may be the only solution. It's really hard to imagine when you get something that's this densely populated to figure out how you're going to retreat. Is that going to happen in our lifetime? I think most people would say sea level is going to continue to rise. Can you build a wall high enough around here to protect them? But structures is one way to do it. One of the things, again, that hasn't been included in the Intergovernmental Panel on Climate Change estimates is anything changing in Greenland. So this is the sort of seasonal areas of melting in Greenland. In 1992, this is what it was in 2002, and this is what it is in 2005. So it's things like this and what we've seen in the Arctic that are sort of surprising even the climate people. Things are proceeding faster than what anybody expected. And so it is a big uncertainty about how fast these kind of things may happen. If Greenland either breaks up or melts, and again, we don't need to have it melt because if this becomes an ice cube, it still raises the level of water in the glass. So if that happened to Greenland, sea level could rise 24 feet. That's a number that's often thrown out. I think that's sort of pushing the envelope a bit, but this is going along faster than people had anticipated. So armoring is another form of adaptation. I mentioned before about 10% of the whole coast, 110 miles, has now been armored. Some of you may live on the coast, have seawalls or revetments. Costs today to build structures like this range from about $3,000 a foot to $10,000 a foot. So it's expensive, and some of this, I would say from the public's point of view, isn't particularly desirable, but we've built a lot of structures trying to protect, in some cases, public property, in some cases, private property. But the impacts or the perceived impacts of armoring have led to more and more hesitancy on the part of the California Coastal Commission to grant permits for new structures. That's an area that I've been working on for the last 20 years or so, is seawalls and what works and what doesn't and what impacts they have. And some of the obvious impacts are visual. This isn't a natural coastline. Some people think it looks fine, perhaps, and many times the property owners who live here don't see it, but the beachgoers do. Access restrictions. This is a big deal with the Coastal Commission. If one builds a structure that keeps people from either getting down to the beach, in fact, we can build a structure that allows people to get down easier if we put stairs into it, or what we call lateral access. If during a high tide you can't get along this beach, Coastal Commission isn't happy about that. Another issue is loss of sand supply. If the erosion of the dune or the bluff or the cliff provides a significant amount of sand to the beach in front of it, and you armor it, your purpose is to stop it from eroding, you're going to cut off some sand. That may or may not be a significant issue. Placement loss, we mean how much of the beach is taken up by the structure. We can build very narrow walls that may take up 1 foot of beach. In this case, we may take up 30 or 40 feet of public beach. That's another concern. Passive and active erosion have to do with passive erosion. As sea level rises and the beach can't retreat because we've fixed this position, over time we're going to gradually flood or drown or inundate that beach. Active erosion is something we've looked at for a number of years. Is do the waves actually reflect off the wall and erode the beach? And we've actually never found that to happen. So those are all adaptations. In addition to that, a bigger issue that's harder to focus on or deal with is mitigation. Can we begin to slow down what's happening and significantly reduce or eliminate the production of greenhouse gases that are leading to the warming of the planet? And as some people have said, we're really not running out of fossil fuels, we're running out of atmosphere. We've got a lot of coal out there. There may be a lot of oil, but that's not solving the problem of more greenhouse gases. And that's a messy topic. So we've been, until recently, the largest producer of carbon dioxide on the planet. China has now equaled us. And I would say for a nation that generally believes in environmental protection, we haven't had a lot of leadership. I'll put something else in there. So that it's been difficult to make change at the national level, but California has tried to be out in front of that. There's been some things that have been denied by the federal government. But California, I think we can all be proud, is seen as a global and national leader. We have had the most ocean-friendly governor this state has ever had, and a lot of states are looking at us to see what we do in terms of our policies for sea level rise and climate change, which I think is a good thing. But one of the reasons that has been given for not taking any action has been that there was an agreement among scientists. I think most scientists say there's probably more agreement on the human impact on climate change than any other modern science question. The second reason that we don't want to try to significantly change our sort of energy use is that would harm the economy. But I think there's a lot of work now being done in California that suggests the economy is going to be harmed in a much greater way. And one of those is California's beaches, in terms of recreation, is a $20 billion a year annual part of the economy. We have the largest coastal economy in the country. If beaches begin to be lost to sea level rises, there's some threats there. There's a lot of issues about diminishing water supplies. Agricultural industry is huge in California, and I think a lot of the allocations of water were developed when we had more water available. And there's a lot of other pieces we could bring in, whether it's drought and forest fires. So it's not simply it's going to be a degree warmer. There's a lot of secondary effects associated with that. So in the end, will it matter what we do? Well, I say because we're the most populous state, we're the 8th largest economy in the world, and seen as a national and a global leader, I think we've been recognized for innovation and discovery. It matters a lot what we do. We have an incredible technological potential. We're visible, so I think we have the opportunity to make some changes, make some decisions that will go far beyond California. And I'm sort of amazed that we've come so far in some areas. You know, we can send vehicles. In fact, we've done this 6 times. We finally found the water. 35 million miles to Mars, drive them around, analyze samples. That's an incredible bit of technology. We now have cell phones that can send photographs around the world. And we have flash drives that seems like once a month they double their capacity, and you buy them for half as much as you did the year before. On the other hand, we're still dependent on fossil fuels for 85% of our energy, most of our electricity. Why is it still cheaper to import 2/3 of our oil? We import about 13 million barrels a day at a cost of $2 billion a day. $2 billion a day. using money we're borrowing from China from politically unstable areas around the world rather than develop something renewable. It's a hard one to kind of understand. And why did the Model T 100 years ago get better mileage than our cars do today? And it also actually ran on other fuels. So on the bright side, there may be some benefits to sea level rise. We could do whale watching in Las Vegas. But I think without question, everything indicates warming is going to continue. The ice caps are probably going to continue to melt. Sea level will keep rising, and that means the shoreline is going to continue to move inland. So many people have said this is the greatest challenge humans have ever faced. There's a lot of technology. I think we can't just say somebody's going to solve it. It's a lot bigger than that. But we really need to move quickly and act decisively, which we really haven't begun to do yet. Some people have looked at the discussion about should we try to reduce emissions by 2020 by 2% or 5%. And some people said that's sort of like driving a car from New York to California and starting to argue about where you're going to park when you get there before you leave on the trip. So we need to make some big changes. My belief is we're all in this together. Everybody has a role to play, whether it's your own personal decisions or whether it's a larger scale involvement. The problem is very real, and I think people would agree the longer we wait to solve it, the more difficult it's going to be to solve. Thank you.